Hi everyone, I'm Evangelos, and today I'm going to talk about our 5G standalone testing framework. This work is in collaboration with Syed, Ahmad, Aanjhan, Roger, and Christina. I would like to go through very quickly because we have heard a lot today. We all know that we have seen a lot of changes since 2G, a lot of new features, applications, and this creates a 5G network that is actually very complicated, and we have to guard every aspect, which is extremely difficult. According to GSMA, these are a few notable examples of security enhancements from LTE. Of course, we have the algorithms, we have integrity support for user plane traffic, expansion of AKA, and SUSI, which is the encryption of IMSI to protect the user equipment. I would like to go through very quickly here, and we all know the architecture. We have the pre-authentication traffic, we have the broadcast messages, RRC connection, and the mutual authentication, the key agreement, and eventually with the security mode command for NAS and AS, we have encryption and integrity protection, potentially. Again, I would like to remind you that only the control plane integrity is mandatory. Unfortunately, even in user plane traffic, it is supported, but it's optional, is up to the operator. I would like to go through the testing frameworks, and there are three categories, I would say. Some of them work on the specifications more than others and have a practical side as well. Others dive into the actual code firmware and try to find vulnerabilities there, and then over the air they can verify that those vulnerabilities actually exist. And then comprehensive and massive testing like dual T test for 4G, to find implementation flaws. So we designed and implemented a 5G standalone setup with core and run. We would like to perform unique 5GSA related tests, make them publicly available, and allow customization, reduce the manual effort as much as possible, increase transparency, and assist manufacturers and vendors. Of course, we want to determine if 5G implementations have actually been improved since LTE, identify products and devices that are less secure than others, and potentially discover new vulnerabilities in the standalone version, including implementation and design. So for the framework components, we have the handler in the middle, which tries to control the entire process of testing. We have the test case, it is loaded, and the modified version of Open5GS and SRS run, it is initialized, and of course we handle the user equipment, and we generate the capture, we capture the traffic, the logs. Eventually, we get all of them together, and we process them and determine the results. For user equipment handling, no routing is required. There are libraries and tools that can be used. We prefer user plane mode because it is faster. Unfortunately, for iOS devices, we need to go and manually handle them. And every time we are resetting the device and the network, so we can get a fresh baseline for the next test. For the evaluation process, we verify that the test case runs successfully first. We collect all the logs, exchange of messages, and we identify the uplink and downlink. And then, based on the expected behavior, we try to determine if the device passed or failed the test. So, very briefly, this image shows how things work. The test case is loaded. The device connects to the network, and once there is an uplink message that the user wants to hijack, a modified downlink message is sent, and potentially the user equipment responds back. And I say potentially because the user equipment may not respond at all. So eventually we get the results, store them, and analyze them. In the code, we have the initial user plane transmission. We determine if there is actually a user input, and then we determine if we want to continue with the normal operations. Otherwise, we map the uplink and downlink, and we send a modified response back. In summary, we modify the NAS and RRC code for uplink and downlink, keep existing function for normal operations before and after the modification. We create new versions of all functions, introduce test case logic, format parsing, initialization of both software and command control. And finally, we try to implement device handling and testing automation as much as possible. This is a representation of an actual test case format. It is separated into 3 parts based on the AKA, and we specify the uplink, downlink, and the command mode, which can be send or replay. And then in the parameters, we have the different parameters of the downlink message that we want to send. We adhere to the actual structure of the messages. This shows the structure of the NAS in plain and protected mode. We do not include or incorporate any kind of malformed messages. We do not send them. And for the testing categories, it is straightforward that we just try to misuse normal messages for demonstration, which mostly are design flaws. Then we have parameter violations, where we change specific values and parameters. And we have security header mismatches. For example, we can send a protected message, but the header says it's plain, and wrongly accepted messages that do not fit in the execution flow and are not protected after the security context. I'll give you an example. Actually, multiple examples. For the NAS protocol, we all know null integrity is very important. We have to test it. IMA, again, before the security context. Then we have the NAS key identifier with illegitimate values, like 0 in this case. We have modified replayed capabilities to reduce the security of the user equipment. We have a non-zero at the binding down values for 5G for the security mode command, and we experimented with different kinds of cause values like N1 mode not allowed and CAG. For RRC, it's kind of the similar logic. We have null integrity again, re-establishment, reconfigurations, and UI capability inquiry before the security context, various uses of RRC release and rejects, and the counter check with invalid MSB values. Our experimental setup is straightforward. We use a laptop with Ubuntu, USRPs, a custom 5G capable SIM card. This can be Sysmacom, for example. And for demonstration only, we use the testing PLMN. There is a mistake over there, but yeah. And before testing, we generate all the unique tests for NAS and RRC, and we make sure that there is a calibration and proper parameterization of the network, because it is very important on 5G setups compared to LTE. SRS Run actually released a tutorial about a GNB connection. Please check it. And these are the only 2 devices that we managed to connect, OnePlus Nord 2 5G and Huawei P40 5G, to our network and perform the test cases so far. I would like to emphasize on one important topic, which is the parameterization with testing PLMN. If we configure the SIM cards with this kind of PLMN, it might be possible for the modems to enter into debug mode and potentially modified security operations. And this will create less accurate results for implementation flaws. What's the solution? Just use commercial configurations in a secluded environment. This is important not only for ongoing research, looking for implementation flaws, but also for already published research. Quick example, for NAS, we have received the registration request, hijacked, and then we want to send the authentication request with the ADI binding down as a random value non-zero, 3131. You can see that nothing else has changed. We haven't modified anything, as you can see, for example, with the NAS key set, and we actually sent this message to the device. And the device responds back with the GMMM status invalid mandatory information, which means it rejected this test case and thus passed the test. For RRC now, we have the registration request, but we hijack actually the setup complete. We want to send the capability in query to get sensitive information before the security context. And actually the device responds back with the capabilities. This is known since LTE and remains the same on 5G. Under 3GPP 38.30.33.1 Annex B .1, the operator is responsible for sending this kind of message, the UE capability inquiry, after the security context, which means that the device does not have the security filters and the proper security standards to reject this message, so it's a failure in this case. In summary, both phones performed really well. We unfortunately didn't find any implementation flaws, solid implementation flaws. For design flaws in misuse of normal messages, yeah, there are many issues. Most of them are inherited from LTE. But I would like to present a few interesting findings. I'm glad that previous presentations have also touched them. And this is the redirection to EPC required 5GS services not allowed. And they show tendency for downgrades. The N1 mode not allowed can lead to the null state, disable 5GS services in the UAE. I would like to mention that messages that send the N1 mode not allowed in the 3GPP access are not required to be integrity protected, and this is a huge problem. For non-3GPP access, though, there must be integrity protection. And finally, we noticed some inconsistencies with SUPI, and this is actually the SUSI null scheme. And the device may reveal the SUPI when it is forced to a 5G network with old SIM cards. We have challenges and limitations, of course. For the framework, automation of evaluation is actually quite difficult. That's because the specifications have a large amount of documents, and in many cases they are very ambiguous, and sometimes they prefer to outsource the behavior of the user equipment to the actual manufacturer. And of course, there can be uncertain UE behavior, and it is very difficult to handle automatically, so we need manual effort. For UE handling, of course, I mentioned earlier that we have the iOS devices. We need to use the airplane mode, for example, manually. And there are limitations in the open source software. because if you want to test some features that are not implemented, you won't be able to do so, and then you have to keep up with every update, which means that you have to change the code every time. For 5G connection based, we need to make sure that we have the correct configurations of the 5G setup. As I mentioned, it's not the same as on LTE, and each device may have different characteristics, making it very difficult to connect. For PLMN configuration, we have another problem here. We figured out that carrier policies are very strict on 5G, which means that there is a white list of PLMNs and 5G capabilities. So our best option is to always use commercial configurations in a secluded environment to avoid any potential issues. Disabling the service 124, which is for SUSE, can always eliminate potential errors, even though you have provided the keys and the routing indicator correctly. You won't be able to see the SUSE, but the rest of the 5G will be untouched. Eventually, we have the lack of debugging tools. This is an issue because we have to use external tools and different kinds of software, commercial and logs in order to determine what is going on very deeply in the user equipment. And sometimes routing is necessary. So for takeaway points, I would like again to mention that we created this 5G standalone framework, but it is not very straightforward. As you can see, we need to have correct testing environment and parameterization, and automation can have limitations. We have the GitHub repo. We are currently updating it. It's not totally ready. And this work is actually a stepping stone for our next projects. So our future work involves updating the framework, adding new features, test with as many devices as possible, and trying to find implementation flaws, and increase the number of test cases for our CNAs, and improve our automation for testing and potentially for evaluation. So thank you very much. I'm ready to answer your questions.
Hi, great talk. I was wondering whether you could go to the slides on UE handling. Slide 6, I guess.
The bullet points, you mean?
Yes, on the bullet point. Yeah, this slide. One more. I mean.
Back?
No, forward.
Okay.
Yes. So, one of the things I was, what do you mean by UE handling? Is it just resetting the UE from the initial state? Is that what you mean by UE handling?
It's for Android devices. It's ADB.
Right.
Okay. Every time we need to create a fresh baseline for the next test case. We don't want the phone to carry any kind of context from previous test case because it's going to bias the results, right? So yes, resetting the device is one of the tasks, and we need to have a USB connection normally with
okay.
ADB and reset it. Yeah.
So for iOS, you said you're doing manually. So what does that entail?
We're talking about not jailbroken iPhone devices.
Okay, so
because there is no ADB or something like that that can help us enough in.
So how do you reset it?
Manually.
Like manually.
Yes.
Airplane mode.
Yeah, unfortunately.
No, but the thing is, like airplane mode doesn't entirely delete all the states until this would require a fresh reboot, right?
Fresh reboot takes a lot of time. So in our case, we determined that airplane mode is easy enough to
but
actually.
Yeah, the airplane mode doesn't delete all the states. That's the issue. I mean, you need a network side intervention to actually force the UE to kill all the states.
Yeah, we actually, as I said earlier, we are doing the refresh both on the network and the user equipment completely, but we are also using airplane mode.
Okay, thank you.
The entire framework needs to be reset.
Right.
I just want to be clear.
Okay, perfect, thank you.
So when you look at like test, we talk to like a stateful, all the options are being handled. So we talked about many of the requirements of the testing. Can you talk about what are the, what coverage you have, and how many test cases you did?
Oh, you mean our coverage in terms of
Yeah.
So we're not using any engine generator to actually generate thousands of test cases, right? We didn't like this idea at this moment because it generates a lot of redundant test cases, and it takes so much time, wastes time, and most of them may not have security meaning at all. So we manually went through the specifications and designed the test cases. And in total, we approximately tested around 80 test cases, both for RRC and NAS. And we covered different kinds of, as I said earlier, we covered different kinds of categories. But we want to expand, of course.
But is your testing stateful or not?
What do you mean by
stateful? Means there could be different vulnerabilities in the different stage of the protocol, right?
Yes.
So because it's a UE and a network, and they will compute the key, then there could be some vulnerabilities after computing the key, right?
Yeah, of course.
So did you implement all the statefulness? Okay. Because I didn't see actually how you implemented the state transitions and those kind of things. That's why.
Yeah, I know, but thanks.
I think that there is one more question.
All right, this is a really neat framework. Thanks for your work. Hopefully we'll end up using this locally in our lab. You mentioned firmware in a previous slide. So one of the reasons that we got away from over-the-air testing was for many of the issues of the manual resets, et cetera. So, but we didn't connect things to a larger, to a core and a RAM. So this is a really neat idea. Have you thought about the potential of using an emulator, that rehosting the firmware into an emulated environment, and then that would allow you to more quickly snapshot and go back to previous results, and potentially tying that into your real-world testing framework?
So actually, we don't want to use any kind of emulation at this point, and we just want to work with the open source software and just out-of-the-box devices. But perhaps in the future.
All right. So let's thank the speaker.